We all depend on resources like oil and gas, but if you ever stop to think about how we actually find this stuff, it's buried, miles beneath our feet. For decades, it's been a game of educated guesswork, a ton of expensive drilling, and just keeping your fingers crossed. But what if you could get a high-definition map of what's down there before you ever break ground? Okay, let's dive right into that. So the challenge is just immense, right? Geologists are hunting for these very specific formations, sometimes no bigger than a football stadium, but they're thousands of feet down. Traditional methods, they give you clues, sure, but drilling a single exploratory well can set you back millions. It's this high-stakes gamble where coming up with a dry hole is a really, really costly failure. But that whole game is starting to change. There's a groundbreaking technology coming on the scene that offers a totally new way to see beneath the Earth's surface. We're talking incredible precision. It's like creating a 3D blueprint of what's hiding in the deep. It's called AFSIP 3D. Yeah, it's a bit of a mouthful, I know, but let's break it down. It basically uses a powerful electromagnetic pulse to sound out the Earth, kind of like how a bat uses sonar. Then it listens for the echo and analyzes how different rock layers react to that energy. The result? A super detailed 3D map. You should really think of it as a geological MRI. So what's powering this geological MRI? Well, the engine is a magnetohydrodynamic generator, or an MHD generator. This piece of tech creates this massive but very controlled electrical pulse. It's like a superpowered flashbulb that's strong enough to go miles into the Earth's crust. And that powerful pulse is what gives us the echo we need to map everything out. The process itself is actually pretty simple in concept. First, that MHD generator fires its powerful electromagnetic field into the ground. Step 2, a whole network of sensors spread out across the surface listens for the returning signals, those echoes from the deep. And finally, and this is the most important part, the system analyzes 3 very specific characteristics of that echo to hunt for the telltale signs of hydrocarbons.
But, how do you turn a bunch of complex electrical signals into a clear, actionable treasure map? Well, this is where some seriously cutting-edge data processing comes into play.
AFSIP 3D's real secret sauce is its ability to measure 3 distinct geological fingerprints all at the same time. First up is resistivity, which is basically how much a rock layer resists electricity. Then you've got anisotropy, which tells us if that resistance changes depending on the direction. And finally, polarizability, which is how well a layer can hold an electrical charge, almost like a tiny natural battery.
But the real magic isn't in any single one of these clues. No, it's in how they work together. The secret weapon of this whole method is something called the coincidence anomaly. And here's the big discovery. When you see weird readings or anomalies in both polarizability and anisotropy in the exact same spot, that is a massive flashing sign pointing to the presence of oil or gas.
And what's so cool about this slide is how it shows you exactly what I'm talking about. On the left, you've got the polarizability data. On the right, anisotropy. See where those highlighted boxes line up perfectly across the different survey lines? That's it. That's the coincidence anomaly. You have 2 different measurements basically screaming, hey, look right here.
Now, the brain behind this whole operation is a software complex called RALPH-1. It takes all this raw data and solves what's known as the inverse problem. So it's like hearing a very specific echo in a canyon and then being able to calculate the exact shape and material of the canyon wall that made that sound. The software works backward from the signal to build the final super detailed 3D model.
Okay, so this quote from Shannon's theorem looks incredibly complicated. I get it. But the core idea is actually brilliant. Think of it like this. You're trying to listen to one person's conversation in a loud, crowded stadium. This mathematical principle acts like the ultimate noise-canceling filter. It gets rid of all the background noise so you only hear the one voice you care about. It makes sure the final map is built on a clear signal, not just random geological static.
The theory sounds amazing, right? But does it actually, find anything? Let's jump into some real-world case studies and see how this thing goes from a cool concept to a major discovery.
First up, we're looking at the Antonin 1 gas field in Poland. Now here, the technology did exactly what you'd hope. It confirmed the known gas potential in 2 specific layers, the dolomite and Rotliegend formations. But then it did something pretty remarkable. It found overlooked potential in the upper granite layer, a type of rock that geologists would normally just write off. This is huge. It shows the technology isn't just for confirming what you already suspect. It's for finding treasure in places nobody else is even looking. Just take a look at this number. 40 to 50 million tons. That is an enormous amount of energy. So where did a discovery of this scale actually happen?
Well, that brings us to the Dmitrievsky License Area over in Russia. By combining the AFSIP 3D data with existing 2D seismic surveys, geologists were able to map out a massive field. The estimate? 40 to 50 million tons of recoverable hydrocarbons. That is an absolute game changer for the entire region.
But finding a massive reserve is one thing. The real trick is knowing exactly where to put the drill to get to it. And this is where OSIP 3D really truly shines.
So let's zoom in on that Dmitrievsky project. The team surveyed this huge area. We're talking over 30 square kilometers. They laid down multiple survey lines to collect data across the entire license block.
And this right here, this is the payoff. Out of that entire 30 square kilometer area, all the complex modeling, all the analysis pointed to one single critical spot, line 9. It gave the engineers a definitive X marks the spot. It took a massive search area and turned it into a precise, actionable target. And the precision goes even deeper than that. The method is so sensitive, it can clearly tell the difference between a productive oil deposit, a worthless pocket of salt water, and the solid granite basement rock. And that ability to tell things apart is what slashes the financial risk of drilling. It stops companies from spending millions on a well that comes up empty.
You know, the results in Russia were so conclusive and the economic potential was so significant that the Kurgan region government officially endorsed the whole project. That's a powerful seal of approval for this technology and its findings.
So, this technology is completely changing the game for finding oil and gas, but it leaves us with a really fascinating question for the future. We have this powerful new tool for seeing into the Earth. If we can create these incredibly precise maps, what else should we be looking for? Critical minerals for green tech? Untapped sources of geothermal energy? Maybe even hidden reservoirs of fresh water? The blueprint is now in our hands. The only question is, what are we going to choose to build with it?